Hello friends, welcome back to my YouTube channel MS Maths. In this video, I will discuss series of real numbers. This is the part 2. You can watch my previous videos of real analysis and group theory and its basic on YouTube channel playlist. Now, we'll discuss the part 2 of this series of real analysis. Real numbers, like series of real number. Okay. Then basically in this video I'll discuss convergence of series, p-test, comparison test, and convergence of series. Okay, so using that convergence like p-test and comparison and real number test, how can we identify that my series with a given series of real number is a convergent or not? We'll discuss these types of important result in this particular video. Okay, so first of all we'll start with the look. Okay, I'll recap you that what is the series and what is the series of real number. That is what the summation of an. If you have any sequence of an, okay, if you have any sequence and if you are adding all the terms of sequence, then that is nothing but a series. Okay, and in series the convergency that we are identifying using SOPS, that is what the sum of like sequence of sum of partial sum, SOPS, that we are identify using that. Using SOPS, that we can also determine that my series is also like series is convergent or divergent together with the sequence of sum of partial like sum of partial terms. Okay, so if Sn, let's say, I will start with the definition. Let's say summation of an is series of positive term, then series either convergent or divergent but not oscillate. But in the case of sequence may oscillate. Okay, there are three cases in the sequence, like either it may be convergent, divergent, or it may be oscillate. But here series will not oscillate. Okay, so the series sum of like convergency means that the sum of series is a finite number, or otherwise it's not finite. That's we are going to discuss here. So the sum of sequence of partial sum is either convergent or divergent. This is what one of the case that I will discuss here called SOPS. Okay. So what is the meaning of this? That necessary and sufficient condition of this, that I will explain you here. That what is the meaning of like sum of SOPS and sum of series of convergency. So from here that I will start with this condition that we have a sequence in which that is Sn and let's say my yes, so like basically the sequence of partial sum is either convergent or divergent. Okay, yes, so in the previous that we have discussed up to the sum of the series. Now here, what is the meaning of SOPS? That we'll see here. So basically, for necessary and sufficient condition, okay, I'll tell you the SOPS. What is the concept of SOPS? Before, like by using the necessary and sufficient condition, we'll proceed with this criteria, with this condition. We'll identify like what is the necessary and sufficient condition for this, so that we can proceed with the convergency. So a positive term series either convergent or like this. So like in this case, let's say we have Sn. So what is the meaning of Sn? Means that a1 plus a2 plus a3 up to an. It is nothing but the sum of this, and sum of sequence either. So it is basically either we can say convergent, okay, and let's say divergent. Okay, not and, convergent or divergent. Convergent or divergent. Okay, so from here, what is the necessary and like necessary condition, not sufficient? This is what the necessary condition, that this should happen, then after we can say that my series will convergent or not. So from the series we'll make a sequence, that is what the sequence of partial sum, SOPS. Okay, so let an is convergent, an is converging to L, and Sn be the sequence of partial sum, then this sequence will converge to L. Okay, so it means that an is a series which is converging to L. It means that SOPS of this sequence, okay, SOPS of this sequence is also converging. This is nothing but a sequence of this, sequence of Sn. It means sequence of sum will also converge to L. Now, what is the sequence of that? That we'll find here, and how this will like ensure that this is only the convergence condition. So what is this? An is nothing but Sn minus Sn minus 1. Okay, and if we'll apply the limit, so limit an is equals to, so from here limit an is equals to limit Sn minus limit Sn minus 1, and from here that we know that this is also, this is 1 and this is 1. So for sequence, if you have any sequence of Sn and if you are applying the limit of for that and tending to infinity, if it is n, then it is the result that the limit n tending to infinity of Sn minus 1 or Sn plus 1, this both will go to n. So from here that we can say this series is, this limit is like, let's say this limit is limit to an and tending to infinity, it is also going to be zeros, and this ensures that this is the necessary condition. So it means if limit of an is not equals to 0, then we can say that it is not convergent. Okay, this is for just for discarding the options. Okay, so if this is not equals to 0, then we can say that limit is not convergent. But from here we can say that not necessarily a convergent. There are a big difference with this. If my limit of this if this an is equals to 0, then convergence, this series, this, okay, if it is not equals to 0, then it is not convergent. Then from here I can say it is 100% divergent series. But if it is equals to 0, then I will proceed to the test of series, and then I will use that test. Then I can say now it is eligible. This is the eligibility, that it is a convergent or not convergent. We'll take example. Let's say we'll take one example. Let's say we have summation 1 by n, where an is nothing but 1 upon n. Now we will just find 1 by n. Okay, so limit n tending to infinity, 1 by n is nothing but 0. Okay, and from here also we can also say 1 by n plus 1, this is also n minus infinity, and this is also n tending to infinity, this will go to 0. Now from here, if we will say that this is nothing but a series, okay, if it is it is nothing but a series, so now from here this is going to be divergent, because of that here limit of an is 0, but okay, wait, but the sum of this series, see, it is what, 1 plus 1 by 2 plus 1 by 3 up to 1 upon infinity, and this will not equals to 0. This sum is not equals to 0. Okay, now I will show you by one example, that we can take one more example. What is the SOPS? That first of all I will explain that thing. SOPS, what is the meaning of SOPS? Just leave it. Yes. Now, what is the meaning? First, write the series. It is nothing but what? 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 up to 1 by infinity. Okay. S1 is 1, means sum of first term. S2 means 1 plus 1 by 2. S3 means 1 plus 1 by 2 plus 1 by 3. Like this. So what is Sn? That is nothing but 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 up to 1 by n. Okay, to 1 by n. So from here it is nothing but what? 3 by 2. It is nothing but 1 plus, or let's say 3 by 2 plus 1 by 3, that is nothing but 3. Okay, like 6 here, then we can write here 9 plus 2. It means 11 by 6. And it is nothing but going to be some quantity. So from here we can say it is what? 1. Okay, now write the series. Sorry, write the sequence. Write the sequence of Sn. It means that S1, S2, S3 up to Sn. Whatever you have, find the sum. This is called as partial sum. So it is 1, 3 by 2, 1 by 16, 1 by 6. And if we'll solve this sequence is nothing but divergent. If we'll find this sequence has some pattern like this. 1 plus, okay, what is the pattern? Like 1 plus 2, 1 plus 1 plus 2 plus 1 plus 3. And next, what is the last term? That is 1 plus 1 by 2 plus 1 by 3 up to 1 by n. If you see this, it is going to be infinity. It means that this capital N is going to be infinity. Means this is divergent. So the series AN is also divergent. This is the concept of SOPS, means sequence of partial sum. Okay. Now, using the p-test, now we will have some more tests that we'll find using that, how the p-test will work, and using the p-test, we can find the convergency of the series. If you have any of the sequence like 1 over p, okay, where p is greater than of 1, where p is greater than of 1, then like p is greater than or equal 1, I think so. P is greater than or equal 1. In that case, yes, p can be greater than or equal 1. If you have any of the sequence like this, okay, then for like this test will applicable for that type of sequence. So for example, if it is summation 1, let's say I will write 1 by n square, 1 by n cube, let's say 2 by n cube, let's say 1 plus 1 by n cube. Okay, so identify either it is a convergent or divergent. Now, how can we check this? See, whenever you will have this type of sequence like 1 n power p, then just if your from here, if your p greater than 1, then it is convergent. It's a simple criteria. So from here, just compare. I will compare with n power p, and from here I'm getting p is equals to 2, which is greater than of 1. It means this is convergent. What about this? If it is sequence n power cube, so from here I'll compare, then I will get p is equals to 3, which is greater than of 1. So it is nothing but convergent. Okay. So from here I can directly write it is what 2 and summation 1 by n cube, and it is what convergent. Again, see this, it is what summation 1 plus summation 1 upon n cube. Now here it is what summation constant. This is convergent. This series is convergent, but it is what constant. Now what is the sum? What is the meaning of this 1 plus 1 plus 1? It is going to be infinity, because start from 1 to infinity. So this constant series, constant sequence is always divergent. Now you can take a note from here. You can take a note that what is the note? That constant sequence is convergent, but series is divergent. Okay. So from here, constant sequence, let's say summation of c, this is convergent, but this is sorry, I have just written, yes, this is going to be divergent. This is divergent, but this is convergent. Okay. So this is what one of the observation from here. Okay. So this is what the p test. This is called p test. Now we'll see comparison test. So this is only for positive term series. Okay. Only for positive term series. If you have any, let an and bn be two positive term series, then an is less than of bn. If two positive term series like an is less than of bn, or some multiple less than of bn, then we can say that bn is convergent, then an is also convergent. Bn is divergent, an is also divergent. Means convergence, divergence together. This is known as convergence, divergence together. Okay, convergence, divergence together. I will take one example for this. Okay, I will first explain what are the cases here. Let an and bn are the positive term series such that the limit of an upon bn, which is finite, which is L, means L here, which is finite, means it is not equals to 0 and it is not equals to infinity. L is finite positive number. We can say finite positive number, or not finite positive, or let's say any negative number, but it should not equals to infinity. Sorry, it should not equals to infinity and 0. This is the basic criteria. It should not equals to infinity and 0. Okay, next, summation of bn is convergent. So in this case, if summation of bn is convergent, divergent, this implies, double implies that this is also convergent and divergent. If bn is convergent, then my series is also convergent. If bn is divergent, then my series is also divergent. Now, next case. limit an bn is going to be 0. Now limit an bn is, now that in that case that was not equals to 0 and infinity. Now my limit is infinity, sorry, limit is 0. This limit is 0. It means bn convergent, an is also convergent. Now an divergent, then bn divergent. See this here, from here bn convergent, then an is convergent. But if an divergent, then bn divergent. This is the case here. Next we have what? Limit an by bn, it's infinity, then an convergent. Now just opposite. So from here an convergent, then bn convergent. But bn divergent, then my an is also divergent. And also this is one of the this is also one of the cases, that is what an plus bn, sorry, an plus 1 upon an is less than bn plus 1 upon bn. Then also we can say that bn convergent, then an convergent. Okay, then an divergent, then bn is also divergent. Okay, so now we'll take example and we'll check using these properties how this will satisfy the things. We'll take example one by one. Okay, so question number 1. Let's say we will have some this kind of uh, okay, some this kind of thing. Let's say if it is summation, okay, 1 upon 1 into 2 into 3 plus 3 upon 2 into 3 into 4 plus 5 upon 3 into 4 into 5. Okay, if it is like this, then what will happen? So what is the meaning of this? First write the nth term. It means what is my sequence, sorry, what is my series? That is what? 2n minus 1, okay, divided by, it is what? n plus 1, n plus 2. Just see here, n is equals to 1. Okay, n is equals to 1. If it is 1, then it is what? N is equals to 2, then it is 3. So 4 minus 1, it is 3. So it is my series. Now what is the first criteria? So we have to choose one b here. Now let's say my an is nothing but 2n minus 1 upon n plus 1, n plus 2. Now what should be the bn, so that I can compare from it? Now bn choose in such a way that the degree, take the degree of denominator. That is what? 1 by n cube. Only the degree. 1 by, just remove the constants and multiply them. That is n cube. Now it is an and bn. Okay, now it is what? an and bn. So from here take this an divide by, okay, from here just take this an divide by bn, and then take the limit of this. Okay, limit and tending to infinity of this. So from here it is what? 2n minus 1, it is n into n plus 1, it is n plus 2. It means that, and we are dividing bn, that is what? n cube upon n. So from here I can directly write, it is nothing but 2n minus 1. I can take n common here and n common here. So it is n cube, and it is 1 plus 1 by n. It is what? 2 plus 1 by n into n cube. So this will going to be, now here it is what? Limit and tending to infinity. So from here again it will say like this, if it is n cube and it is also n cube. So this is nothing but 2n minus 1, okay, divide by, it is your 1 plus 1 by n, 2 plus 1 by n. Okay, and now if you are saying that n tending to infinity, then it is what? It is going to be infinity. It is going to be infinity. So yes, so this is going to be infinity. See this is going to be infinity. Now come here, an by bn is going to be infinity. Okay, so an by bn is going to be infinity. So bn is divergent, then an is divergent. See here, my bn is divergent, but from this we can't find any of the conclusion. See, from this we can't find any of the conclusion. Why? Because of that we have only the case that if it is infinity, then if an is convergent, then you can say my bn is convergent. Whatever in denominator, that is convergent. But here we are identifying an, so just take it as n square, not greater than of this. Now take it as n square. Now if it is n square, then it is n square, then it is n square. Now it means here it is n. Now if it is n, then you can write like this. Okay, I'll explain one more time this question. So if it is n, then 2 minus 1 by n, and it is 1, 1 plus 1 by n, 2 plus 1 by n. Now if it is what? It is n tending to infinity, it is going to be what? 2. Okay, this will go 0, 1, and this is 2. So it will be 1 from here. Now if it is, wait, sorry, it is 1 plus 2 by n, 1 plus 2 by n, 1 plus 2 by n. Okay, so from here it is 1 plus 2 by n, and it is again 1. So it is 2, means now it is not equals to 0. Now if it is not equals to 0, means this case. So if bn is convergent, then an is also convergent. See here, what is my bn? That is n square. It means from here p is greater than of 1, means bn is convergent. So if summation bn is convergent, it means summation an is also convergent. Now, what was the problem with n cube? Okay, so the problem with n cube is that we were getting what? We were getting infinity. But you can see in infinity, what? In infinity, we can only discard the thing. If we are taking bn as divergent, then we can say an is divergent. But we can't make any of the conclusion because our bn was convergent. Let's see. See here, our bn is convergent because it was n cube. Just maximum you can take like this. Maximum you can take, remove the constant and multiply. That's the simple criteria. Okay. One more question that I will explain to you. Let's say one more question like this. Summation 1 upon n power p plus q by n. Okay, if it is the question, then we'll take bn. Okay, so from here an is nothing but 1 upon n power p plus q by n. What is bn? So bn is nothing but 1 upon p. Just take this. If it is 1 by p, then just take the ratio. If it is an by bn, and take the limit n tending to infinity, then what is this? 1 upon n power p into n power q by n divided by 1 upon n power p. This will go. So it is n power q by n, and this is nothing but n power q power n, and it is if limit n tending to infinity, and you know that if it is n power n, then this will be infinity, or it is infinite, sorry, it will be 1, infinity power infinity. So if it is 1, means it is not equals to 0, not equals to infinity. Now if this will get convergent, and of course this will convergent. Okay, if this will get convergent, it means if p is greater than 1, then see, if p is greater than 1, then summation 1 upon n power p is convergent. So summation 1 upon n power p plus q by n is also convergent. This is the simple case here. Okay. Next, we can take one more example from here. Let's say if we have any of the sequence like this, series like this. Example, summation n square plus n plus 1 upon n power 4. Okay, let's say n power 4 plus 1. Okay, then what is bn? Bn is 1 upon n square. You can take bn n power 4 also. You can take bn as n power 4. But remember, okay, one more thing that you can remember. Highest power is what? 2. Highest power is what? 4. Then 4 minus 2. Denominator's power minus this. Then you will get exactly that. From here you can also see. From here you can also see. Highest power, or let's say degree is 3, and it is 1. So 3 minus 1, you can take this. So you will get always you will get the correct. Always you will get that. This is one of the result here. Okay. So 4 minus 2, that is 2. Then take this as 2. Now it's just use that concept. Limit n tending to infinity an, that is n square plus n plus 1 upon n power 4 plus 1 into n square is 1. Then take, what is this? N square. Take n square common, then 1 plus 1 by n plus 1 by n square. And from here it is what? N power 4, then 1 plus 1 by n power 4 into n square. So from here this will get cancelled. And if you will apply this, then this will be 0, this will be 0, this will be 0, so you will get it as 1. So not equals to 0, not equals to infinity. It means that whatever my bn here, that is n power 2, if p is greater than 1, then of course it is convergent. Okay, so my series an is also convergent. So this is the concept of this particular video, okay, this particular topic. So I hope you are getting this concept or you understood. So thanks for watching my video. Keep watching MS Maths. Please like the video, share the video, and subscribe the channel. Thank you. Bye bye.